Okay, what if I told you that a single type of chemical bond is the secret behind a life-saving antibiotic, a hormone your body literally can't live without, and the stuff that makes surgery possible? We're diving into the world of haloalkanes and haloarenes. And I know, it sounds super complex, but by the end of this, you're going to see the simple chemical trick that makes them so incredibly powerful.
I mean, just look at this list. We're talking about chloramphenicol, which fights off nasty things like typhoid fever, or thyroxine, the hormone that keeps our metabolism in check, and even halothane, used in anesthesia. These are not some obscure chemicals in a lab. They are, quite literally, lifesavers that are fundamental to modern medicine.
So, what's the secret sauce here? What in the world connects a hormone to an anesthetic to an antibiotic? Well, it all comes down to one simple but incredibly powerful addition to their structure: a halogen atom. You know, fluorine, chlorine, bromine, or iodine from the periodic table. Sticking one of those on a molecule changes everything. So, how do we get from a simple chemical bond to a life-saving drug? Well, here's our game plan. First, we're going to dissect the anatomy of these compounds. Then, we'll sort them out into their family tree. After that, we'll crack open their reaction playbook, which includes a tale of two very different kinds of attacks. And finally, we'll tie it all back to why this chemistry is so important.
All right, let's get into it. Section 1, the anatomy of a halo compound. To really understand what makes these guys tick, we've got to zoom way in on the one part that matters most: that special bond between the carbon and the halogen, which chemists call the CX bond. And you know what? The definition is just beautifully simple. You start with a basic hydrocarbon, just a molecule of carbon and hydrogen, and you just swap one of those little hydrogens for a halogen. That's it. That one little swap creates a whole new world of molecules, a haloalkane or a haloarene.
And this is where the magic happens. That halogen atom, it's super electron greedy. It just hoards the electrons in the bond it shares with carbon. This little tug of war leaves the carbon atom slightly electron poor, giving it what we call a partial positive charge. You can basically think of it as a glowing "attack here" sign for other molecules. This one feature, this polarization, is the key to pretty much all of their reactions.
Now, not all halogen bonds are created equal. As we move down the periodic table from fluorine to iodine, the halogen atoms get bigger and bigger. You can see it right here in the data. The bond length gets longer. And at the same time, look at the bond energy. That's how strong the bond is. It goes down. This is absolutely critical. It means a carbon-iodine bond is way longer and weaker than a carbon-fluorine bond, which makes iodine a much easier target to kick out in a chemical reaction.
Okay, Section 2, sorting the family tree. Now that we know the basic building block, we need a way to organize the huge variety of these compounds. And chemists, well, they love to organize. They do it by looking at the halogen's immediate neighborhood.
So at the very top, the family splits in two, and it all depends on the type of carbon that the halogen is attached to. On one side, you've got haloalkanes, where the halogen is on a carbon in a flexible, kind of chain-like structure. On the other side, you've got haloarenes, where it's bonded directly to a carbon that's part of a rigid, flat, aromatic ring. That simple difference between chain and ring changes their behavior completely.
Now let's dive into the haloalkane branch. Here, it's all about location, location, location. We classify them by how crowded that carbon holding the halogen is. Is it attached to just one other carbon? That's primary. Two others? Secondary. Three? You guessed it, tertiary. And then you have some special cases, like allylic and benzylic halides, where being next door to a double bond or a ring gives them some extra stability.
And on the other side of the family, we have compounds where the halogen is bonded directly to a different kind of carbon, an sp2 carbon. If that carbon is part of a simple double bond, we call it a vinylic halide. If it's part of an aromatic ring, it's an aryl halide. The key word here is directly, and that placement makes them a lot less reactive than their haloalkane cousins.
All right, Section 3, the reaction playbook. We've met all the family members, now let's see how they act. What happens when these molecules actually get into a chemical reaction? It's time to open up their playbook. So, the star play for haloalkanes is called nucleophilic substitution. Remember that carbon atom that was a little bit positive? Well, it's a target. Something called a nucleophile, which is basically just a species that loves positive charges because it has extra electrons to share, comes in, attacks that carbon, and kicks the halogen right out. It's a simple swap, but how it happens is just fascinating.
And this brings us to Section 4, a tale of two attacks. See, this substitution can happen in two very different ways, which chemists call SN1 and SN2.
You can think of them as two completely distinct strategies for an attack, and the strategy they choose has huge consequences for the outcome.
Okay, let's break down these two strategies. The SN2 is like a single, swift ambush. The attacker and the target are involved at the exact same time, so it works best on uncrowded primary targets, where there's less stuff in the way. The SN1, on the other hand, is a more patient two-step play. First, the halogen leaves all on its own. Then the attacker comes in. This works best on bulky, tertiary targets that are stable enough to wait around. And as we're about to see, these different approaches lead to wildly different 3D outcomes.
And here is that SN2 attack in action. It's so cool. The attacker, the nucleophile, has to approach from the back, totally opposite from the halogen it's about to kick out. As it pushes its way in, it forces the entire molecule to flip inside out, just like an umbrella in a big gust of wind. This perfect inversion is the absolute signature of an SN2 reaction.
Now, for the SN1 reaction, the story is totally different. Step 1, the halogen just leaves. That's the slow step. This creates an intermediate called a carbocation, which is totally flat, like a pancake. Now, because it's flat, the incoming attacker isn't picky at all. It can attack from the top or from the bottom, which leads to a mix of different products.
Now, to understand why these different outcomes are so important, we need to quickly talk about something called chirality, which is basically handedness. Just look at your hands. They're mirror images of each other, right? But you can't lay one perfectly on top of the other. They're non-superimposable. That means they are chiral. A vase, on the other hand, is superimposable on its mirror image. It's achiral. Well, a ton of molecules are just like our hands.
In chemistry, these non-superimposable mirror image molecules have a special name, enantiomers. You can think of them as the left-handed and right-handed version of the exact same molecule. Now, why does this matter for our SN1 and SN2 reactions? Because even though they are almost identical, our bodies can often tell the difference, just like a left-handed glove only fits on a left hand. In biology, the 3D shape is everything.
And that brings us to our last section, why this chemistry matters. So we've talked about umbrella flips, flat intermediates, handedness. Why does any of this matter outside of a chemistry lab? Well, because controlling these tiny, tiny details is how we go from a chemical blueprint to a life-saving breakthrough.
Knowing the rules of SN1 and SN2 turns chemists into molecular architects. They can choose a specific starting material, like a primary or a tertiary one, and then select just the right conditions to force a reaction down one path or the other. This gives them precise control to build the exact molecule they need, with the exact 3D shape required for it to work as, say, a new drug.
But there is a flip side. That super strong carbon-halogen bond that chemists love to work with, well, it can also be a curse. As this quote points out, that same stability means these compounds are incredibly resistant to breaking down in nature. They can persist in the environment for decades, sometimes even centuries.
And this really leaves us with a critical question. We have these amazing chemical tools that have enabled incredible progress in medicine and all sorts of industries, but they come with a lasting environmental footprint. So the challenge for modern chemistry, and for all of us, really, is how do we balance the power of creation with the responsibility for its consequences?